Okay, let's look at the example of pendulum, except rather than hanging by a string, it's hanging by a spring. So this gives us an extra degree of freedom, right? Or a couple, right? So yeah, we'll just use Lagrangian mechanics to figure this thing out. All right, so a few details. So L is the length of the spring when it's just the natural length of the spring, right? Okay, just when there's no mass on there. X is the additional displacement of this mass along the spring's axis. So it's just how much the spring has been stretched or compressed. And of course, theta is just the angle that this pendulum makes with the vertical. All right? And of course, this spring will have a constant K, a spring constant K. All right? I guess I'll write that in there just to, all right, to have it down. Okay, so let's start off. Right, we're going to use Lagrange's equation, the Euler-Lagrange equation, to get the equations of motion for this thing. And to do that, we need to know the Lagrangian. All right, and so to do that, we need to know the kinetic energies and the potential energies, right? As expressed in the different, the generalized coordinates. In this case, it's going to be x and theta. All right, so starting off, let's look at the kinetic energy. All right, so if we were to hold theta constant, we would have kinetic energy just in this x direction. All right, so that one's fairly easy. 1/2 m x dot, so the velocity in x direction squared. All right, and if we were to hold x constant, we won't hold it at 0, but we'll hold it at some constant. We would have a kinetic energy in due to the swinging of the pendulum, right? So that's just going to be a 1/2 m. All right, and the velocity here is just going to be the same as r theta dot. Since I'm running out of space anyway, let's just introduce an r real quick. All right, this we squared. All right, so r is just the total distance from this point down to this mass. So we're not going to use r, so let's go ahead and write this out. Leave a little bit more space this time. All right, just so we know where that came from. All right, so I'm just going to distribute this square into here. So we have, in this case, it's an L plus x. All right, that's the distance here, L plus x squared and a theta dot squared. Okay, so there we go. There's our kinetic energy. All right, the potential energy, we are going to have a contribution from the spring. All right, the potential energy stored in a spring is 1/2 k x squared, where x is just the displacement from equilibrium. All right, and okay, now one tricky point here when we do the gravitational potential energy, I'm always tempted to, call the 0 point of our gravitational potential energy down here where the mass reaches its lowest point, and then have positive values for potential energy up from there. All right. I run into hot water when I do that in this problem. The reason being, when theta equals 0, the mass can still move. All right, so basically the angular part brings the potential energy to 0, even though the mass can be basically anywhere, as long as the spring allows it, to compress or to stretch out, right? So that's it just doesn't work. So instead, let's take our 0 for gravitational potential energy here at the fixed point up here. So we're going to have a negative potential energy for all of these, for the whole motion, right? All right, so basically, so we'll have the minus sign, right? There's going to be this, the length of this, which again is r, but which is equal to L plus x. All right, there's a cosine of theta. All right, so this will give us the h part of our mgh. Now we just have to add mg. Okay. All right. So I think we're good here. Okay. So let's go ahead and write out the whole Lagrangian. So here we go. We just want a t minus a v, and so we'll write out our kinetic energy first. 1/2 mx dot squared from right here, plus 1/2 m L plus x squared theta dot squared from right here. Now we're going to subtract these two off, so we get a minus 1/2 kx squared, and then we'll have a plus sign on this, plus L plus x cosine of theta multiplied by mg. All right, so here we go. Here's our Lagrangian. Now we can dive into using the Euler-Lagrange equation to get our equations of motion. All right, so Euler-Lagrange equation. We have a partial derivative in here with respect to, okay, so let's just write them both out. Why not? There's one for x and one for theta. Okay, so one for x, one for theta, we'll end up with two equations of motion. Great. So let's start with x, why don't we? So first, I always like to do the inside piece here and this piece, and then so let's just start assembling some pieces here. So first I'm going to find the derivative of this Lagrangian, the partial derivative of this Lagrangian with respect to x dot, all right? So velocity in the x direction. All right, we have, so this one's just mx double dot, right? Wait, no, excuse me. Gee, there's no double dot on this yet. All right, so there's just one dot here. All right. Let my mind wander there for a second. All right, and that's the only x dot that appears in this, so we're good there. All right, let's go ahead and find the partial Lagrangian with respect to x. So this piece, all right. We have an x here, an x here, and an x here, so this one's going to be a little bit longer. Okay, so here we go. So we have, bring this 2 down, we have an m L plus x, all right, take the derivative of the inside, we just get 1. Theta dot squared, all right, now we'll take the derivative here, so 2 comes down again, so we just have a minus kx. And then here on the end, we throw out the L, and the x just gives us a 1, and we end up with an mg cosine of theta. All right, that is so good. I'll scribble all these out and just put one big dot on top. That might make it easier to see. All right, so now what we're going to do is take the total time derivative of this partial derivative with respect to x dot. So this piece that we found already, we're just going to put that in here like this, and now we get our mx double dot. All right, so maybe we can use a separate piece of paper real quick for equations of motion. All right, so the first one we're going to do is, why not just bring this over to the other side and make it positive? So we'll just set this part equal to, this part, all right? And I'm gonna go ahead and divide by the mass as well, all right? So this equals this, but divide by the mass. So dividing by the mass, we just have an x double dot. All right, and now here, divide by the mass, we have an L plus X and a theta dot squared. And now we have a minus K over M X, and then a plus G cosine of theta. All right, here we go. So there's our first equation of motion. We'll come back to that. Now let's look at the theta side of things. So here we have our Lagrangian again. I'm going to go just like before, and first we'll find the derivative, the partial derivative with respect to theta dot this time. So scanning through here, we see 1 theta dot. All right. Try and keep all of this in the frame. Okay. So we're just taking the derivative here. So the 2 is going to come down again, cancel the 1/2, L plus X squared, and we just have 1 power of theta dot left. Now we take the derivative of the Lagrangian with respect to theta. No theta here, no theta here, no theta here. There's our theta right here. Okay, so the derivative of cosine theta is minus sine theta. All right, so there will be a minus here. We'll have our L plus X. We'll have our mg, and then a sine of theta. All right? Okay, so now we want to take our total derivative with respect to time of this thing. All right, so the things we have to worry about here are, so the m won't depend on time in this problem, and the L won't depend on time, but x and theta dot will. All right, so all those other little pieces will go to 0, whatever. So we're going to have some constants out front. All right, so let's do the easy part first and just have a theta double dot multiplied by L plus X squared. Okay, now, so we're just doing the product rule, right? All right, we took the derivative with respect to this. Now I need to take the derivative with respect to that. I get a 2 L plus X, okay? And then taking the time derivative of what's inside, there's L is a constant, that won't matter. We get an X dot. And now we have our theta dot here on the outside. All right, so we'll go through and write our second equation of motion. Again, let's just divide by the mass. And we're just going to set this equal to this, just like before. All right, so just bringing this piece right here over to the other side and making it positive. Okay, all right, so yeah, go ahead and divide by the mass. we have a theta double dot, I'm looking right here, L plus x squared plus 2 L plus x dot theta dot going to be equal to this right here, which is minus L plus x mg sine of theta. Okay. All right, so crossing my fingers here, hoping I didn't make any mistakes. Let's just, so here we have our equations of motion. Real quick, let's just go through and double check what would happen if we if we get rid of all the x, or we get rid of all the theta. Can we recover the cases of, just a simple pendulum on a string, or just a simple mass on a spring? Let's see if we can recover those two cases. All right. So case. So let's just say x. We're going to set all of the x parts equal to 0. Let's see what we get. All right. So looking up here at this one, I have 0 equals, okay, so there's, this x goes to 0. We're left with L theta dot squared. This part goes to 0, plus g cosine of theta. Okay, and this one, we have a theta dot L squared. This will all go to 0 because of this x dot, and equal to minus L m g sine of theta. Okay, so first off, this one's a bit confusing, and I don't think I have a very good answer for it. It could be that I made a mistake somewhere. But what this gives us is this. So this is just the radial acceleration, right, for a circular motion. All right, this minus sign is the part that confuses me. I mean, you can make sense, as theta goes to 0, right? You just get g, the full value of g, as it reaches its lowest point. All right, so that's perfectly lined up with the radial direction. All right, so that part, magnitude-wise, this makes sense to me. I'm not sure about this minus sign, so it may be worthwhile to go back and check on that, because I mean, yeah, you'd think g is positive, right? Theta dot squared is, has to be positive, and L is positive. So anyway, maybe we somehow ended up on the wrong part of our cosine theta or something. All right, so I'm not gonna worry too much about that one because I don't really know. All right, but dividing both sides of this by oops. Oh, why do I still have an m? Oh. All right, I divided this by m, so this m should not be here. Okay. All right. Okay, should have checked for that. All right. What do we got here? So this m is not here. All right. We have a minus g over L sine of theta. All right, so this is the classical pendulum equation, right? So for very small angles, very close to 0, sine of theta is going to be very close to theta itself. So small angles, All right. So for small angles, this reduces down to a simple harmonic oscillator equation. All right, and which is just like I shouldn't use x. I'll just use z. Z rod equals minus omega squared z. All right. So here are the frequency of oscillation at this small angle is equal to g over L under square root. All right, classic pendulum. All right, so that part, except for this confusing minus sign, that part seems to check out. And we also found that extra mass in our equations of motion. So, all right, so great. And a case that I hope will not be quite as confusing is when we set all of our theta pieces to 0, right? So it's not moving at all in the theta direction, and we should be able to just recover Hooke's law. Okay, where did my equations of motion go? Here they are. Okay, so all theta parts go to 0. So here we have x double dot. All right, this piece goes to 0 because of this theta, equals minus k over mx. So we're off to a good start. And this part goes to 0. All right. Well, yeah, I guess it depends on where you set your theta. There could be offset by a constant here. Okay. I guess we set the theta to 0, so all right, fine, we'll put that in there. Okay, so this part goes to 0, this part goes to 0, and sine of theta, thankfully, is 0 here, so our other equation just doesn't tell us anything. Okay. Well, if I were to add these forces, or add the mass back in, or multiply by the mass back through, all right, so we could just do a classic Newton's second law, right? Sum of forces equals m a, or m double x, all right? So the x double dot, I mean, so this is just multiplying by the mass equals minus kx plus mg. Okay. So I think I may be beginning to understand why we had that minus sign. Okay. And I think it's because back when we defined our x, we defined this direction to be positive. So when it's pointing straight down like this, the positive direction is actually downward, all right? So I think that's where our minus sign confusion came from on our, wherever the heck it went. This guy, so this minus sign, right? It's a little bit confusing because of just the direction I defined my x. Maybe I should have defined it differently. So anyway, I think if we search there, that's where we'll find the explanation for this minus sign. Aside from that, what we have here is just a spring, all right? So here's the Hooke's law force, and here's the gravitational force, and so, like we said, the L, right, that we used, x is the displacement from the natural spring length L when there is no mass on it. All right. So if we had used for L, rather, if we had used the natural length of the spring when it's all stretched out here, then we wouldn't get this this term. So basically, if the spring by the mass of this, by the weight of this mass, isn't being stretched beyond its normal linear range, basically you can redefine a new place of equilibrium, all right, and the spring should still obey Hooke's law with respect to that point. So then, in that case, we define a new point of 0 and a new displacement from that point, which I will call x prime. Okay, this is a little cluttered, all right, but defining this new displacement, and assuming the spring's well behaved, so k is not like changing, and anyway, basically you can get this just the simple harmonic oscillator again. Okay, so with a frequency of k over m under square root. All right, so I think the equations of motion that we got work well. So I think these things check out. Like, now that I've erased this mass here, right? I think these things check out. We get it's a little bit awkward just the way we defined our variables, right? With the x in this direction, so on and so forth. We ended up with that one weird minus sign. We ended up with not accounting for the weight of the mass in our at when theta goes to 0, things like that. But you just kind of have to, I guess, pick your battles as far as what parts of the problem you want to be more convenient, depending on how you define your variables. So yeah, I think this still works out.